In this video, we explain the phase diagram for water. Okay, when we were looking at diagrams that represent the molar Gibbs energy versus temperature at constant pressure, okay, we learned that water had a special behavior. Okay, the lines are like this. That's the solid, that is the liquid, and this is the gas. Okay, where that would be the boiling point. And now we understand that this boiling point occurs if the vapor pressure of the liquid is identical to the external pressure. And then this is the fusion point, or freezing point. Then what we learn is how this graph would change if we increase the pressure. Okay, so if we draw this at a pressure P2 larger than the pressure P1, then we learn the following. Okay, this line is going to be offset by an amount proportional to the molar volume, and then these lines are also going to be offset towards higher values of the molar Gibbs energy, but the offsets are going to be different from the rest of the substances in that for the solid, the molar volume is greater than for the liquid, and only that only happens for water among the substance that we're interested in. Okay, so the offset of the solid line is going to be greater than the offset of the liquid line. Okay, like that. Okay, what that means is that the near boiling point is shifted up with pressure, that's the prime, but the near freezing point right here is actually depressed. And that is exactly backwards of what happens with the rest of substances. So the question is, well, how does this affect the phase diagram? Okay, notice that for most substances, the way that we have drawn the phase diagrams are like this. Okay, you have this is where the liquid is, that's where the gas is, this is where the solid is, that is the critical point, that is the triple point. And we can see how this knowledge that we derive actually pans out. Okay, so take any boiling point, this one, and see what happens to the boiling point when you increase the pressure. Well, this is the pressure that we have, this boiling point. If we increase the pressure, then the boiling point is going to increase as well. Okay, so yes, the boiling point goes up when you increase the pressure. That makes sense, and that happens for both water and the rest of the substances. But what happens for the freezing point? Well, for most substances, what happens is that when you increase the pressure, okay, you go up, then the freezing point goes up, the temperature goes up. But for water, this should be backwards. Notice that here we're increasing the pressure, but the freezing point gets depressed. So clearly that does not capture correctly the phase diagram for water. Okay, so the phase diagram for water is going to be like this instead. Okay, you can have pressure versus temperature. Okay, that's the gas, the solid, and the liquid. This part of the diagram is going to be the same, but what is different is this other part. In this particular case, the slope of this line should actually be negative in order to make sense with that depression of the freezing point with increasing pressure that we actually have explained in class and that it happens in nature. Okay, notice that when you have a negative slope right here, what happens is the following. This will be your freezing point at a particular pressure, okay, but if you increase the pressure, so suppose that you go from this pressure to that one, you're increasing the pressure, then the freezing point goes down, okay, gets depressed. Okay, which is exactly what we know what happens for water. Okay, so for water, again, notice that the slope of that line is actually negative compared to the rest of the substances. Now, this also has an interesting consequence, and that is that, well, for most substances, the temperature of the triple point sets the lowest temperature at which the liquid can exist. It's no longer true for water. Notice that for water, the liquid phase can exist at temperatures below the triple point. Okay? The pressure of the triple point still determines the lowest pressure at which the liquid can exist in both. Okay, but notice that the temperature is no longer the case. Right. We'll actually learn more about this negative slope of this solid to liquid phase boundary a little bit later on. Okay, and just to wrap up things here up, okay, we've already said that the critical point for water, this takes place at 218 atms. 647 Kelvin. Okay, this triple point is at about 373.2 Kelvin, and then the pressure is very low. Pressure is equal to 0.006 atm. Okay, so it's kind of difficult to see where that ripple point is because you need specialized equipment that can take you to pressures that are about 6,000ths of an atmosphere. Okay. Now, something that is also quite interesting about water, and it happens also for many substances, is that the solid part of the diagram is actually quite different from what we have right here. Okay, it turns out that people have described upwards of 15 different solids that you can have water in. Okay, so this is just where you're simplifying this part of the diagram considerably by saying that there's only one solid phase, but in reality, when you actually take a look at these diagrams, they have up to 15 phases up here at conditions of high pressure and so forth. Okay? Alright, so that's the phase diagram for water and why is it different from the rest of the substances.